I guess I can just start. Hey everyone, welcome to this session, prototyping an EIP in Geth, like a case, EIP-3074 case study. My name is Ansgar, and I am part of the Quilt team at Consensus. So we, as a team, a couple of months ago, I think it was what, let's see, the EIP is from October of last year. So basically, a couple of months ago, we came up with this EIP-3074. And part of that process of developing the EIP, we also wanted to, of course, get some experience with it, with the actual behavior, play around with it a little bit. And so we ended up prototyping it in Geth. We had done that in the past with other EIPs as well. And so since then, we've just been kind of like trying to kind of like get this EIP through the governance process. Right now, it's basically being discussed. But when basically the question was if I wanted to present something here, I felt like maybe actually taking this whole process, like taking the EIP from the idea all the way through like the prototyping to the end product that you can actually use, might just be like a really interesting thing to do. And so the goal for today would really be to just like basically take an hour and implement this EIP from scratch. So like start with vanilla Geth and just see if we can get all the way through. That might mean it's a little bit experimental. I don't know if this will be interesting to watch. I mean, I hope so. But it'll, of course, just be very specific to this EIP. But I still think like having an actual full end-to-end picture, right? Because a lot of the time, people only talk about specific aspects. But then I usually, as someone in the audience, was always left with the question here, but how do you tie all of it together? So I kind of try to really go this end-to-end approach here. And so just in the beginning, I wanted to take just like 2-3 minutes, talk about the EIP, just so you have like a rough understanding. If you don't know the EIP yet, it's probably will be all a bit quick. So maybe then afterwards, if you want to look into it a bit more, you can always do that. But just as like a quick primer on this. So you know how in Solidity, there's just like a random snippet or a transfer function in Solidity, how a lot of the time basically the authentication works just via message.sender, right? So you just look who called into me and grant them access, basically. What that means is that most users, of course, I mean, in an ideal world, everyone would use smart contract wallets, and they would have a lot of functionality. In the world we're living right now, most people just use MetaMask or whatever, and they just have what we call an externally owned account, EOA. So that's just an account that doesn't have any code attached with it, just a private key. And so if you want to do any action from that account, basically all you can do is just send a transaction from that account to, let's say, Uniswap. But then it can only do, like, it can only basically call into one entry point. So you can only perform one action per transaction. And so our goal was to basically give smart contract functionality to EOAs. And the way we did this was with these two opcodes that we introduced, and we are going to implement both of them. So the first one is called auth, and the second one is authcall. And so the idea is we have this new concept that's called an invoker contract. And the invoker contract would first take in a signature. So if I have an EOA, I sign a message that authorizes this, contract. And then it would basically check with the auth opcode. It would check the signature, and if the signature was valid, basically the invoker contract would be authorized to send calls in my name. And so then the invoker contract could, for example, do on Uniswap. It could first do like an authorize and then a transfer. Things that usually take 2 transactions on chain now would only take 1 transaction, because with the one signature you could authorize both, and then the auth call is the actual opcode that then goes out and basically impersonates the signer of the signature to do the call. And so last thing here, basically, this is the actual message that is being signed, and we need that in a second when we actually implement it. So the important thing here is just that like you sign over the invoker. So like you only grant access to this one specific contract. They can impersonate you. Like no one can just lift the signature out and use it with their own contract or whatever. And also, we want it to be as generalized as possible. So like we only see what is like a 32-byte commit. And the idea is, of course, that this is like a hash commitment to some validity constraints or something like that. But again, from the implementation point of view, we only deal with what we call a commit value. That we'll just treat that as 32 bytes of random data. And so that's, again, like if you don't know the EIP yet. Oh, yeah, sorry, go ahead.
Does that mean chain ID will be secure?
Yeah, so there's been a conversation around that, whether chain ID is needed. It's not technically needed. There are ways around it. You can put the chain ID in there, and then there's some ways of making it work without chain ID. We are currently in the process of probably moving to a version where chain ID would be part of the signature. So this is a really good question, actually. So this has been raised, and yeah, so we'll likely move, but we'll implement the old version that does not have chain ID. Mm-hmm.
Is there any reason not to have a chain ID?
Well, this is like a bit of a philosophical question, maybe a little bit out of scope. So the question is, the idea is you might want to have use cases where you authorize like a specific type of invoker across chains. So yeah, but again, like it's a hard trade-off. We probably like I don't want to make it a final decision here, but like it looks like we might just end up enshrining the chain ID as part of this. But this has been like a topic of active discussion. And as well, like this presentation is not supposed to be an endorsement of the AP. I mean, of course, as one of the authors, I'm a little bit biased here. But it's literally just taking it as an example. And like we're just trying to implement it and prototype it. And the nice thing is, the idea is you should be able to just prototype whatever idea comes to your head. And most of them will never end up making it on chain, right? So whether this will ever make it to the chain, who knows? It's really just like as an example of something worthwhile to do here. And so with that, first just a point that's not supposed to be like the ending slide. So there's just like a pointer to, we also have like a full talk on 3074. So if you want to learn more about the EIP itself, just come to our talk tomorrow at ECC. And our talk, that's Matt over here, and mine. And of course, also, by the way, shout out to Sam Wilson, who unfortunately couldn't be here, but who's the main brain behind the AP, I would say. OK, and then with that, just last thing, disclaimer, this is really only prototyping. I wouldn't say I'm like a good Go developer, but the whole point is to show you that like just as long as you have some basic programming skills, this is really not magic. It's really easy to do. But of course, there's a world of difference between prototyping and then actual production implementation, right? So just want to be very clear here, because otherwise the Geth team will hate me for this. OK, and then if you actually want to follow along, I'm not sure, it might be a little bit quick today, because of course, I mean, I only have 80 minutes to work with, some of which is already gone. So it might be relatively quick, but if you just want to follow along a little bit or something, or if you like watch this recording, or if maybe some of you afterwards watch this recording, you can like, I put some of the resources on here. If any resources they are missing, feel free to like ping me, and I'll just raise it now or whatever. But I'll also like show this, and I'm not sure. Yeah, I think that was my last slide here, so I can actually go ahead and show you. So this is this UL. This is just over here. So this has like only like a few very basic resources that we need to basically get going. And with that, I think I'll just sit here for most of the talk, because of the recording. So let's just kind of naively get going here, basically. So first things first, of course, we'll go ahead and just have the vanilla Go Ethereum repository. We would just clone this. I created like a fork. So, but this is still, as you can see, we are even with Ethereum master. So this is like a completely untouched fork. And then we would just clone this, because I wasn't sure about like the quality of the internet. I already went ahead and cloned this. So, so if we just go to here, as you can see, we have a completely untouched version of the repository. And then I know this is kind of like a little bit controversial. So like some people like to use minimal dev tools. I like to go with a more beefy IDE. So if that's not your thing, apologies. But I'll just stick with whatever I feel most comfortable with. So here we are. And so what I wanted to start with before we actually implement the IP, I briefly wanted to like introduce like our test case at the end. So the idea is, once we have it implemented, we want to spin up a local testnet and actually run a 3074 transaction. So I want to do that already now, just to have you see the transaction fail, so we know what like the goal here is. So first thing is we just want to, of course, I don't yet have a Geth, so like let's make Geth actually, and I hope this works. Oh yeah, so what I can do is actually maybe the easiest thing could be to just go for this. Does that make a difference? Huh? Bigger? Even bigger? Okay, let's see. Yeah, but I just wanted to, because then I want to have like all text be bigger. So if that's big, otherwise I can manually. OK, so but yeah, feel free to like, because I can only see my own display, and that's big enough. So, but of course this is like a relatively small. I mean, it's big amount of it. Yeah, you get my point. So we now we should be able to have Geth. Yeah, I already pre-added that to my path. So now we want to actually create a local chain, and I think like on the workshop thingy, I added some instructions. So if you want to actually do this, go ahead and do all of this on your own. So basically, first thing what you do is we want to actually so let's go here, and let's just so this is just like the repo, and then let's actually create a new account. Let's not give this a password because I trust all of you. And so now we have a key. We want to have this be the signer of our testnet. So then we go ahead and we modify our Genesis file to actually, because we'll just use proof of authority for our testnet. Oh, sorry. So we just want to set this up for Genesis for the signer here. You would, of course, do this with your own address. And that way, we give it some initial balance, and then it's also the signer for the testnet. And then all we have to do is just initialize the chain like this, hopefully. Yep. And then we can just, well, we can almost get going. We only need one more thing. We need to actually unlock the account. So here we have the account unlocked. And then, oh, wait, that's not what I wanted to do. Sorry about that. Oh yeah, I guess I could also just do this. Looks good. Okay, so let me just briefly. Yeah, I have like a secondary. Yeah, I have a secondary user account, which apparently doesn't have my usual setup. I only use that for streaming, and I don't stream, so that's why it's not set up. Yeah, that's what I was thinking. Okay, so now we should have a testnet running. And so now if we actually go ahead and and that should also be linked here. So there's this remix version that supports 3074. So if we visit this, and text might be really small here, but we don't really do a lot here, so it should be fine. And we just connect to our Web3 provider. Awesome. Then we can just go ahead and workshop, just import our test contracts. So we have 2 test contracts that we need. The first is the actual invoker. Let's.
Did you get the remix version that?
Oh yeah. So we kind of in our work for 3074, we also forked remix, and we also forked Solidity to support 3074. That was out of scope for this workshop, so I can have another workshop of prototyping EIPs and Solidity. That's not for today though. So like basically we just use the existing fork versions. You can find all of that under like if you just Google, I don't know, Quilt EIP-3074, you find like our fork versions of Solidity and everything. But yeah, this is just out of scope for now. But we basically just have this remix.pushy.quilt.link. This is just where you can find the remix version that's compatible with 3074.
Can you give a sense of how much work it is with that? Like, can it take you 5 minutes or more like 3 days?
I would say like both the initial kind of prototyping Geth and like the forking of Solidity is both kind of a day each, I would say. Like, I mean, now of course it's quicker now for our Geth fork, but because we already know what exactly to modify. But when you're figuring that out on the go, it's more like a day, and similar with Solidity as well. I felt like, because I only added support within Yule in Solidity, so it's easier because then you just only have to specify the opcode itself, which is relatively simple. So if you can read anything here, basically all the contract does is it just kind of forwards a call, and it does the simplest thing. So it uses an empty commit. It also doesn't forward any call data. It's just a raw call that gets you pass in a signature and an address, and it just proxies that call. So this is like the simplest invoker you could possibly write. And then in order to actually have something to use the invoker with, I also have this super tiny contract here, which just like basically lets you kind of acquire ownership of the contract. So if we compile this now with the special EIP-3074 version of Solidity, and now we just deploy it. So we just deploy Hello World Invoker and also the own me contract. We'll arrive in Geth in like just a second, so bear with me here. So now we have this OMI contract, right? And the owner initially is unset. And once I send a transaction from my Geth, just my vanilla Geth account, 389 whatever, then that's set as the owner. But now if I would want to use the invoker, and that's why all of this work, we can just use this in hopefully in an hour just to then see everything work. So this is why it's not useless. So we just give it like a fake signature and the address, and we want to transact, then it gives us an error, of course, and the error is invalid opcode F6 is not defined. And so what could F6 be? Well, that should be auth, but it doesn't know auth yet, so this execution fails. So now basically our goal is to teach it F6 and also F7, which will be authcall, and then hopefully it should work. So if we just open the EIP for a second, so auth F6, and authcall F7. These are our targets. So now, actually, like after all of this, let's maybe first stop the chain because we don't really need a chain running of the whole time, and let's actually go implement something. Ideally, of course, you should have like some general overview already of like how Geth roughly is structured. I feel like that's also mostly out of scope for a year. So basically, the idea is just like you go look through the code a little bit, you identify the locations where you want to make changes, and then you go in and make changes. And so in this case, all we want to do is modify the core EVM behavior. So almost all of our work will be within the core VM package. And then in here, the nice thing is the way it's structured, it already has an EIPs.go where they kind of add all the latest EIPs. So we'll just kind of add ours in here as well. And we can just be really naive about it. So let me start, and we can see, okay, we have some activators here. So ideally, we would want to be in there as well. So let's say 3074 wants to be in here as well. Enable 3074. And of course, we have to actually implement enable 3074. So if we just go all the way to the bottom, you can see all these different EIPs, and we just want to have one of these as well. So let's just go ahead and enable 3074. Let's just write this function. And we want to have an opcode that's called auth. So it doesn't know the auth opcode. So maybe we should actually teach it what auth is. Also, I won't write any comments because that just slows me down too much to fit this into one session. This, of course, even for prototyping, you shouldn't do that. But oh well. OK, so first things first, we have to actually teach the Geth what auth and authcall actually is. So let's just go ahead and have a look at where all the opcodes are defined. So that seems to be in the opcodes.go. And I already know that like the opcodes I want to do is F6 and F7. That happens to be directly after create2. So I'll just go and create 2. Oh, and also I realized, let me just, because I didn't actually start a screen recording, I wanted to also do a screen recording of the talk. So let me just, right. And given that we have still 95% of the, well, 90% of the talk left. Capture entire screen? Capture. I guess it just works. No, that's a screenshot. Yeah, OK. Should have thought that through. New screen record. Oh, and then just like record entire screen. Yeah, that sounded way better actually. Record. Bam. OK, now we can just continue. So as I was just saying, we just now arrived in Geth, where we right now want to actually teach it about our auth opcodes. So now we have defined auth and authcall. And all that does is just kind of like gives it the mapping of like the actual byte value for the opcodes. So at least that looks nice now. And so now we actually have to go through and define the operation properly. Right now it uses this op-base fee where we stole it from. For execution, of course, we don't want that. This should be op-auth, which doesn't exist yet. And this should be op-authcall, which also doesn't exist yet. And then let's look at some of the details. So what's the gas cost of the opcode? Well, for that, we actually have to look back at the EIP. So our auth opcode, and of course, all of this, if you haven't looked at the EIP, you don't know yet. So you just basically have to follow along here a little bit. But like as you can see, we have a gas cost section here where we just say the gas cost for auth is 3,100. So just like a constant, there's no dynamic part. So we just have to, we could just put in 3,100 directly, but of course this is like not, it doesn't look nice. So if we just look through it here, usually that what happens is that you just define like a nice parameter, like a constant that we just then use. So let us actually do auth gas EIP-3074 and set this to the value that we want. So 3,100. And with that, we are off and running. And so now last things here is the stack behavior. If we go look at the EIP again, we can see that it takes 4 elements from the stack. It returns 1. And this is all that we need here. So basically, it pops 4, pushes 1, pops 4, pushes 1. Boom. So basically, I mean, we kind of didn't yet define the opcode itself yet, but at least all the shell is here. So now if we just give it an empty behavior for now, so we just have an op-auth that doesn't do anything, then technically we fully implemented op-auth. Yeah, I mean, we actually will give it the proper behavior in a second. Same thing, of course, with authcall. So let's first give it an auth, give it like a shell. And then we have to look at the gas cost. So the nice thing with authcall just basically, again, does one of these authorized calls, but we already have a call opcode. And our authcall is very similar in behavior to the normal call. So as you can see, authcall is interpreted the same as call, except for, and then a couple exceptions. But importantly, the the static cost is the same. So like it just so happens that the constant gas cost for the call opcode was recently adjusted in EIP-3074. So we just steal this, and this will just be our constant gas. Now, authcall is a little bit more complex, so it doesn't. The operation kind of struct defines quite a few fields. So we just go in there. It also defines dynamic gas and some of these other flags. And so we actually have to define a little bit more. And importantly, we can just basically have a look how call is implemented. So again, I'm jumping around a little bit, but yeah, the idea is really just to give you all an idea of like how you could end up working in here. So basically, as we can see, for dynamic gas, it actually has its own nice little function. So we give it that as well. And then, of course, we don't want it to be Geth call, but Geth auth call. And then we actually have to end up defining this, of course. So where's Geth call defined? Over here. So let's just steal this. And maybe, I don't know, after static call looks about right, or maybe at the very bottom. OK, let's just call this Geth auth call. And of course, likely we'll have to modify it a little bit, but for now, this just works. So let's just make a note here. OK. And then the stack behavior, if we just go back to the EIP, we can see that we have 8 items, 0 to 7 that we pop, and 1 that we return. So same thing here, same thing here. And then last things that the call opcode does is it also has like it also has to specify the memory size, because return data can actually increase the memory, overall memory size, and also it also changes the call data, so the return data, I mean. So these 2 flags have to be in there as well. And we don't actually want to do memory call, but we want to have another memory auth call. But the nice thing is we can just, this one we can just immediately adjust, because it's really simple, because the only difference between our auth call and the normal call is that we kind of snuck in another stack element here that just isn't in there for the normal call. So we just have to offset all of these values by 1. So instead of 5, 6, we have 6, 7, and instead of 3, 4, we have 4, 5. And then our memory auth call is already fully functional. And so, kind of like just to kind of have the first. Let's maybe even kind of like, while we're at it, let's just see, because now we kind of gave it a shell. Of course, what still we didn't do, we didn't define the dynamic gas portion of auth call. We also didn't actually implement the 2 EIPs, but at least we basically already put the shell of the EIP in here. And so what we can already just briefly check, we can just see if Geth still compiles, which ideally it should. And it does, so looking good. So maybe let's just briefly commit this. Let's just say core VM params, let's say initial EIP-3074 commit. OK. Oh, wait, and then I just was about to commit that to master, and of course, you shouldn't do that. So let's just have a workshop branch. See, OK, let's try this again.
Thanks for that review. Thanks for that review.
Yeah. That was so. I mean, luckily we are like on my private fork anyway, so I wouldn't have actually tried to push to, and I don't have push access to, and for good reason, as you might notice. Yeah. So don't ever give me push access to your repo.
EIP is not live.
The EIP is not live yet. Well, I mean, it isn't enabled here either, so technically it wouldn't hurt to have that be pushed to master, but you kind of don't want to have rubbish in your code. OK, so let's now basically the only steps that are like lift. So and this will be our 4 other commits for the day. Will just be implement auth, implement authcall, adjust the gas cost, and then actually create a fork for our EIP, have it enabled, and retest our transaction from the beginning. That's the rest of the program. And then the first opcode, the auth, it's a little bit technical because all we do is just like validate the signature and stuff. So for that part, I also have to probably cheat a little bit and have my phone where I did that in the past. So it's kind of from scratch, but also like with some memory help. But basically, this one will be like the most, the most complex kind of just opcode logic-wise. So let's just get going though. So first thing that an opcode usually does is just kind of grabs the elements that it needs from stack. So this time around we need 4 elements. So if we just go back to the opcode, it has commit, and then maybe I'll just call this v because that's easier inside Geth because that's usually how it's been called. So let's just say commit vrs. Let's just grab that from stack. So commit vrs. We just grab, and that just will be scope stack pop. We just pop this from stack, and we do this for all 4. So like this should be good. So now we have the opcodes. And then, so the way auth, the behavior of auth is basically, the idea is, I think I showed you in the presentation earlier the structure of the signature. So what we want to do is we basically get the commit. We want to first assemble this whole message, right? Then we want, so basically including this type byte, and then the invoker address, and then the actual commit. Then we want to hash it together. And then we want to do an easy recover, where we also construct the signature, and then basically put this together, and then just do the check. And then the result, if we indeed get a valid address back, we want to save this in a special context variable that's this authorized account. That has to be like a context variable that stays with us for the rest of the context execution, because then all auth calls use that as the from address. So first thing I want to do for that is to actually like add to the scope element, add like a field that we can use for this authorized address. So let's just give this another field that's type common.address. And we can just use this here. So first thing we want to do is we want to clear this in case there was something else in there already. So we do just scope, oops, not that, scope authorized is nil. And then we will do our actual check and optionally recover it, but we'll do that as last step. First, what we want to do is we want to actually take the result and put it back on the stack, right? And for efficiency reasons, we don't want to create a new stack element, but we just want to reuse one. So I'll just call it temp, just a renaming to make sure like we know it's supposed to be a new element. We'll then set the element to whatever we want it to be. So we can't just set it to scope.authorized because that can be nil, but the stack element has to be a number. So if it was nil, basically, we have to manually set it to 0. And the most efficient way of doing that is just with this clear function. And then else, we want to actually just set it to whatever the value was. So just temp dot set bytes 20 of this thing. Dot bytes, I guess. Sounds good. And then we actually want to put this back on the stack. So scope dot stack dot push this temp thingy. And I guess that's that. OK, awesome. So now all we have to do is actually kind of recover the address and everything. So let's do this. So first thing first, where can we find in Geth an existing version that's kind of similar? Well, there's the EC recover precompile. So maybe let's just go ahead and look there. So that happens to be very close in this contracts.go file. We can see that we have the EC recover function here. So first thing that it does is it checks that the v is only a single byte of value. Everything else has to be 0. So that's the first thing we have to do. And it also does this extra validate signatures function. And because it is for historical reasons, EC recover is a little bit more lenient with its rules, we have to be a little bit more strict. So first we have to basically only move forward if. So what we want to do is v dot bitlang has to be smaller than 8, so because it's only a single byte. And we also have to, oh, not and. Yups. Python sneaking in. So we want to give it v and s and with true, but actually v and s are not big integers, but they are a specialized type for efficiency that's kind of even more efficient as stack elements. So we actually have to convert it to a normal big. Big, yeah, where here, too big, exactly. And then, oh no, v of course not. V actually has to be a single byte, but the other two have to be big integers, and v has to be a single byte. So byte v dot, yeah, this, I guess that's the easiest way to go, because we already checked that it has that it's only a UN64. I mean, even smaller than that. Okay, and only in this case do we actually want to try and recover the thing. Again, this whole auth opcode is the most kind of a little bit most tedious, because it we just have to go through the whole process here. But I still felt like using this kind of real world EIP is a more interesting case study, just because it's an actual thing that people want to bring to mainnet rather than just have a toy EIP. I don't know. So I hope that's not too bad. So again, basically what we want to do is we want to actually first construct this whole message here, and then we want to hash it. So let's first allocate this message. So so we have byte array of length 65 because this is 32, this is 32, and then this is 1 byte, so 65 in total. And now let's just fill this. So first thing that we want to put in there is the magic, this kind of magic prefix that just happens to be hex 3. So so the first thing is just this, and then we want to actually copy over the address of the invoker. But of course, the address is only 20 bytes, but we have the padded address, so it's actually we have 12 zeros in the beginning. So let's do this. So let me just briefly, because there are always different ways of copying. So let me just briefly check how to. Oh yeah, exactly. So we just use the copy function. And again, 12 zeros, we already have 1 byte set as well. So we only start at slot 13, we go to 33, and we copy over the, which should be scope.contract. And again, I mean, all of this, the more you deal with Geth, the more you just kind of see where all the things you need, where they're located, basically. So we just use the address, and then I guess the bytes representation. Okay, then we have the invoker address in there as well. And the only thing that's needed is the commit. So commit, and then I think what we can just do is we can just do write to slice, and then message, and then here we are 33 to 65. I think that's basically it. So that's the message, and then we can just hash it. So hash is just the Ketchak of the message. And I guess that just works. So now we have the hash. And now before we can actually, because like if you again look at the easy recover precompile, down here we actually want to do this. So maybe I can already copy this over. So we want to have to give it both the message that was signed over that we just constructed, the message hash, but then also the signature. So we didn't yet actually, we also have to like, for the signature, we also have to put it into like a 65-byte thingy. So let's, so basically what we want to do, this will just be our hash, and then sig we still have to actually build. So let's just do this. It happens to also be 65 bytes because the signature is also 65 bytes, but this is accidental. And then I think the way it wants to have it, though, is that v is at the very end. So let's do this. So let's copy r over first, write to slice, signature from 0 to 32, and then do s, write to slice, sig 32 to 64, and then actually give it v. So sig 64 equals, and then just basically what we did above, so v dot uint. Okay, so this should just kind of like work now. Now we should have the pub key and the error, the potential error, just returned here. And so first we just want to make sure we don't have an error. So if we only continue if error is nil. And in that case, now we want to actually, last thing, and you can also see this in here. So in order to convert a pub key into an address, we still have to do some fancy shuffling here. So this value should now be written to scope.authorized. So scope.authorized should now be, oh wait, we can't actually quite do it this way. So we have to create a new address. So var address, and that should be a common address. And then we just do, so I think the way we have to do it is like this. So basically now we want to copy over into the address this and like everywhere. So this should just work. So now we implemented auth. So that's basically all. I mean, we didn't really test it. I mean, who needs tests? I mean, for prototyping, I don't know. Do tests, don't do tests, whatever works best for you. I just trust my code generally. I think that should work, actually. So I think like our auth implementation just is done here. So we can just, well, first maybe see if it still compiles. Again, this test is somewhat arbitrary because it just checks for syntax errors. Still nice. So, and this time we only touched core VM. And so we implemented auth. And this was like, again, the most kind of tedious of all of the individual operations we have to do. OK, so that part's done. So like auth is now fully done. We have like fully specified it with all the guest costs, everything. We could just basically create a hard fork only for auth. It would already work. The last thing that's missing now, we actually want to use this authorized value that we now set, because otherwise it would be kind of useful, like pointless. So now we actually have to also implement authcall. Yeah, but authcall is, I think, more interesting because there we, of course, already have the existing opauth from the opcall. I mean, from the call opcode. So we can just look at how this looks and copy it over and all these kind of things. So let's try and jump back to where the call function is defined. Here's opcall, and let's just borrow all of this. Why not? So let's just roll this. So I mean, kind of done, but not really. So now our auth call would just behave as a normal call. Would already work, but of course wouldn't be ideal. So now we want to actually modify it the way it has to be modified. So we can just see auth call, and luckily it gives us like a list of it's interpreted the same as call, except for, and now we just have to go through and implement these. So if authorized is unset, execution should be invalid. So the whole execution reverts. So this is kind of just the first thing we can do. And given that we already revert in that case, we don't even have to bother taking elements from the stack because we won't work with the stack any further if execution just reverts. So we can just do that at the very first thing in here. So if scope.authorized is nil, then we want to just throw an error. And so in this case, we actually need a new error. So because, of course, we want to give it the correct reason. So we just jump to where all the errors are defined, and we just define our own. So let's call this unset authorized. And just copy this. And I don't know, authcall authorized unset. OK. And then we just want to throw this error here. So we'll just return nil and unset authorized. OK, so that we implemented. And again, I mean, all of these things, right? Like you specify them, and then it actually only takes a minute to actually also implement it in Geth. It's not really, I don't know. I feel like, yeah, it's really not that hard. So gas cost, again, is something we only deal with as the last thing. So we kind of just ignore those that reference gas cost. Then we have this, there's no gas stipend. So what is a gas stipend? Well, we just glance over here, and we find this value called stipend. That's the same thing. So we just remove it. Done. OK, let's continue. Value is deducted from the balance of the executing contract. Sounds like a normal call. It's not paid by authorized. OK. If value is higher than the balance of the existing contract, execution is invalid. Oh, this is different. So there's another thing that actually throws. So if value is higher than the balance of the executing contract, where's this checked? We can just see here. So basically, this is just like the initial kind of setup of the call, and then the actual check for balance and so on happens inside the EVM.call. So if we go in here, we can see that if value, basically, if it doesn't have enough money to transfer, then it would normally just return this insufficient balance error. So we can just basically test for this when we return. Because usually what the call opcode does is if the internal call failed, it just puts like a 1 on the stack, or a 0 on the stack, just to indicate that the call failed. But now we actually want to throw in this specific case. So what we have to do is like if was this exact error, then we just propagate that up. So we return nil and this error, and then just everything else, just like a big else if. OK, that part is done as well. And then if value x, oh, so we don't have a value x yet. Why again? Yeah, there's this one extra value from the stack. So we actually have to get one extra value from the stack. So let's do this. So here's where the execution gets all the values from stack. So after value, we actually want to get a value x as well. Value x. And that just means we need one more stack pop operation. So stack pop, and boom, and done. So we have this value x now. Now we have to actually also actually use it internally. So we already basically we already convert value into a big val. So let's also convert value x into a big val. So let's also do big val x. And then we just need to do the same efficiency gain thingy here, where we say if value x is not 0, we actually convert it into a big value. OK, all of this just kind of like, yeah, kind of comes naturally. And then let's see. So the only thing that then that's still left, we basically did all the small things for the opcode. The only big thing that we actually now want to implement is the actual main core of the EIP, right? Now, when you do the call, actually set the sender address to the authorized address. That's the whole idea behind the EIP. So that's the one thing we didn't do yet. And if we look again, there's this EVM.call where it just kind of like calls into, and then it does the call internally there. And the unfortunate thing is that only gives in the contract that is the caller. And so in order to actually be able to distinguish between the contract that called, and that's still important for things like where to deduct the send funds from and so on, and then the actual like the thing it should set as the from, we have to modify this call function. And instead of just modifying it, because that's actually quite tedious, we just do the nice and easy thing and just create a copy. So at the end of the file, we'll just create a copy that we'll call authcall. OK, And so instead of call, you're not supposed to do auth call. But we want to pass in the from address. So we'll just do from and addr, here's the to address. So like from and to are both just of type address. And then after value, we also want to pass in value ext. And both of those are big integers. And then, of course, we still have to actually slightly modify its behavior. So where do we get the address from? Well, that's easy. We just use the scope.authorized. So we just do scope.authorized. And then after big val, we also pass in big val ext. Boom. And then like the main kind of the auth call function is already done. But of course, the one last thing that's still missing is we have to actually now do the thing in auth call where we actually do the different behavior. And so looking at this, so there are two things that we still have to do. The first thing is if value ext is non-zero, the instruction immediately returns 0. So like for now, we have this value ext. So basically, the idea is for EIP-3074 that you can send funds, like send ether with a call either from the invoker contract or from the signer contract. But right now, because it's a little bit more complicated, we actually ban sending from the signer contract. So we already have the stack element, but we just don't allow you to use it. So we have to implement this. So directly after checking value, we also just check value ext. So if value ext sign, if that happens to not be 0, you didn't behave well. And so we just have to return an error again. So we also need to create a new error for this. So let's just do the same thing we just did. And let's just call it error non-zero ext value. Oh, value ext, I think. Value ext. OK, auth call non-zero value ext. Boom. And then that part's done. So last thing that's not necessary is just pass in the from at the correct locations. And so we just see where caller is used, and then just see which of those we have to change to from now. So this caller is just used to check where to send the funds from. That one we don't touch. This one here, that's used for the tracer. The tracer actually wants to know where the call kind of like seems to come from. So this is indeed now from. Transfer, again, we don't touch. Tracer, again, we do touch. And last thing is, here's now the actual execution that happens. So it creates this new contract object, and then it uses that to actually run. And so here we want to tell the contract that it was called from somewhere different. And so the simplest thing is, instead of going in and changing the actual constructor, we just do the hacky thing and just say contract. After we instantiate it, we just say contract caller address. It happens to have this field that we need, is from. Boom. And now I think we're done. So basically, that just, done with this step. But this just implemented auth call for us. So we can go ahead and let's maybe do my little, just for the good feeling, the check again. We can compile. So we implemented auth call. Nice. Thanks for that. So what was still missing? Well, we still have this comment here, to do adjust. So the last two things that are still missing is adjust the gas operation, the gas calculation, and then actually create the fork, run the thing, see that it works, be happy. Be happy is optional, but yeah. So let's do this. So let's already be optimistic and remove the comment, and then go in here. So Geth auth call. So what's actually different for our gas calculation? We have to go back in here. And we can see that there are some things. So this is the most important thing. So if the gas available for the subcall would be less than gas, execution is invalid. Normally, if you basically specify how much gas you pass into a call, and normally if you want to pass in a lot but you don't have quite that much, it just gets truncated. But for auth call, because it's a little bit like has to be a little bit more trustless. Otherwise, you could kind of cheat people from their money and whatever. So we actually have to make sure that if you passed in too little gas, it just won't work at all. So this is kind of slightly different behavior. So we have to fully enforce that you get all the gas you pass in for the gas cost. There is no gas stipend. That part we already discussed. And then there's one last thing that I don't see here right now, but it's also important that if you pass in a 0, it actually reverts back to this old behavior of passing in whatever it has. So these are the kind of things we have to change. So first, let's just do the easy thing, which is the stipend. And stipend, you usually get some extra stipend when you call transfers value. So in this case, usually you charge this full 9,000 gas, but that includes a stipend of 2,300. So in our case, we don't want to actually charge the stipend, so we just do the hacky thing again and just remove the stipend. So easy, that part's solved. And so like the last thing now is actually like this slightly different behavior of how much you pass into the call. And this is actually computed in this other function that's called call gas. So this call gas function that does this whole 64th calculation to see how much gas is available to pass into a subcall. And this function now we have to modify. Unfortunately, because it's used for all functions, we can't. It's not easy, not ideal to just copy paste it. So what we'll do is instead we'll pass in a is authorized boolean like this, and then branch on based on this behavior. So all we have to just do is make sure that all existing uses of the function now just pass in false because wait, not is authorized. Sorry, I'm typing. What I want to do is, of course, is authcall. So we want to know if we are if we are inside of an authcall. And of course, in all existing behavior cases, that's not the case. So we just go briefly through and we tell all the existing users of this function that they don't use authcall. And then, of course, our new function is supposed to indeed give in a true here. OK, and now last thing, and then literally we only have to do the actual forking mechanism. But last thing here is just to do this slightly different behavior now. So again, what we want to do is like here's basically the check where it checks that if it basically can't it can't pass in enough gas, then it just basically truncates the gas, and we don't want that. So in case we are so basically, this should only happen if we are not in an auth call. So if we are not in an auth call, that behavior should just continue. But otherwise, we want to fail. So now we want to just return an error. So we return 0 and an error. And the error, again, we have to define. So let's define the last error for the day, which will be error insufficient auth call gas. Okay. Okay. So wait, where were we? Over here. Okay, so now we return an error. And as I was saying as well, so if we pass in a 0, so if it's authcall and we actually pass in a 0, so the call cost that we passed in is 0, then we actually want to instead return whatever is available. So again, this was a bit of a detail. We kind of technically wouldn't have to implement the full gas computation behavior because, I mean, we don't care about it. We won't actually test it. But just to actually have the proper opcode behavior, right? Because now this is actually fully how it should be. And I mean, I'm sure I possibly made a mistake somewhere. Maybe not. Hopefully not. But basically, this is everything. So now we can just say we implemented the gas auth call function. And I do recognize I didn't test if this runs, but I'm just optimistic here.
Is it actually called?
Huh?
I thought you just modified the existing call gas.
Oh yeah, I mean, we implemented auth call, yeah, but by copying the existing function. But like we modified it. Well, no. We did modify this function to have like to remove the stipend and also to pass in like a different flag to the thing.
We modified call gas, but you were saying that you would copy call gas as well and modify it in a separate.
Oh.
Yeah.
No. Yeah, I wanted to say that I don't want to do that because it's easier to just pass in the flag. Okay. So that's why. So basically, that part we did with the flag.
How do you decide at which point you want this as a flag?
I mean, for prototyping, go with whatever. I generally try to just follow the structure. So like usually where every like if call and delegate call and all of these different static call, if they all have different functions already, then I just add another function for auth call.
Okay.
If there was only one function for all of them, I try to keep it that way, basically. But again, just like, I mean, to stress again, this is prototyping. Like, I'm pretty certain in production this would look differently. But basically, this is all. So now, all that's left, though, is to just create a fork. Let's create the Paris fork, because that's where we are. And let's just enable the EIP. So let's also just do the naive thing and trace our way backwards. So, oh, wait, sorry. So basically, this is where we implemented the EIP, enable 3074. So let's just see where like the base fee is activated. So let's just trace this back. Apparently, here we create a London instruction set. So let's maybe create a Paris instruction set. New Paris instruction set. So
for all these changes that you're making, are these in the repo already?
yeah, but I'll also commit like all the changes we just committed. I'll also push it to the repo as well, just so you can see the exact version. But there's like there was a fallback version in case anything went wrong here or today. So there's already a version that has all of them, but I'll also push these as well. So, but the one we actually want to enable here is of course 3074. And then the question is, we could base it on top of London or on top of Berlin. This is just like the question of how do we want this to work. But the thing is that because London introduced 1559 and our remix version is not yet compatible with 1559, we'll just do it on top of Berlin. That's nicer. So we'll stay on top of Berlin. So now the question is, what do we do with this instruction set? Again, we'll just trace our way all the way to the top. It's only a couple of hops. So we'll define this new Paris instruction set, and new Paris instruction set, and then where's the London instruction set used? Well, only here. That's easy, so we just need to add one more case. So we need a chain rule is Paris. That's of course not yet a thing, but it will be a thing in a second. So where do we have is London? Well, just here. So let's just add is Paris over here. And then where is London used or set? Well, down here. So again, is Paris. I mean, the meta point here is of course just that like it's really like easy to do all of this on your own. So if you're someone who like occasionally like dabbles around with new AP IDs, but usually you just like have this theoretical idea, but you don't want to implement it. It's really, I mean, that's why I'm trying to just like do the naive thing here, always just like click on things and just follow. Basically trying to just recreate the exact flow that I would also just normally have if I were like fresh at this as well. So now, of course, we just need to implement is Paris. So like let's do this as well. So is Paris, and that should give us Paris block. Okay, we are getting close because Paris block or London block or Berlin block, those were things that we already specified in the Genesis file. So we're like really close to just having it all work. So we just need to specify a Paris block. Okay, and now this unfortunately breaks a couple things just because here like all the block numbers are specified manually by hand, and so we just have to go ahead and say this is just some test configurations. But for those we just have to manually tell them that they shouldn't have any Paris blocks. So we just like add a nil where the Paris block would be, nil where the Paris block would be, and nil where the Paris block would be, and then all of this unbreaks again. Okay, so
on the tree side, just enable so that we can see the source tree. Thank you.
like this? Yeah. I'm not sure like how well. So we are right now we're in the core VM. We're in the params config. So right now we're basically almost all of the modifications we did so far were in this file. So yep. So basically now we have the Paris block. So now we like last thing is just we have to, for one, I just really like printing this out. So wherever it actually prints out what chain we are on. It's really nice when we run the node to actually see if we are on Paris or not. So let's just add this down here. OK. And then I think that might have been it. So let's just see. Oh, yeah. No, I think we just, I think that's it. OK, awesome. So we just defined the Paris block, and I think let me just try. So let us just let's maybe not yet quite commit because we just want to test if it works first. So let's make another version of Geth. And that version would still be compatible with our existing testnet because the existing testnet did not have Paris enabled, right? So if we just run our Geth version again, and maybe I'll just do it full screen, so then we can see up here. So it says we don't have a London block, and also we don't have a Paris block, which is awesome. So basically, it already knows about Paris. So now all we just do is we just remove the existing chain. So that's just the chain that was without Paris. And now we just add a Paris block. So really easy. In our genesis.json, we just add a Paris block directly at Genesis. And now we just have to initialize. So let's just do geth init one more time. And let's run the chain. And we are apparently on Paris. So of course, doesn't mean anything yet, but that means we can at least now try and use 3074. So ideally, that should just now work. So let's go back to remix. Of course, cancel the old transaction. Let's also maybe just connect fresh, just to be certain. OK, so let's deploy the same two contracts again. OK, that worked. The owner is currently unset. And let's first try it with a dummy signature. Of course, I mean, if this already doesn't work, then we don't even have to try with the full signature. So let's see. OK, it doesn't throw an error immediately, at least. That's nice. So if we just fail to activate, of course, then what it could also so let's just see what's the owner value. I'm not sure if you can if this might be completely too small to read at all, but this is like a 126 address, and of course because we use the fake signature, this is just a random address now. But at least it is not the address of our invoker, and it is also not the address of our full account. So this is kind of looking promising. So now we only have to last thing we just have to do is we have to use like an actual signature, and for that we created a little remix plugin for a signature. So now what it did internally just created a new JavaScript wallet just inside of the browser. The JavaScript wallet is like, that's basically our user. In that case, that will now sign our message. So this should be hopefully the new owner of this contract once we use the real signature. So ideally, our target address now is 160 whatever. So all it needs for the signature is the invoker address. So we just go over, we copy the invoker address. We give that to the signer, and we create the signature. We don't have to put in a commit because the default is already the empty commit that we use. And now we get these values to use. So let me copy them over. So an empty v value, this for r, and this for s. And let's send one more transact. And again, ideally, what we want is this wallet with 160 whatever to appear as the owner. And we have a wallet with the owner with this contract with the owner 160. So indeed, basically, the opcode worked exactly as we wanted it to. Like it recovered the signature of auth, worked exactly as we wanted to, proxied the thing, and so basically like this implementation. Again, you couldn't just open a PR with it against Geth, but it would be close already. Right now, you only have to clean it up. And you're ready, right? And if you ever listen to the authcall call or anything like that, oftentimes, the problem is that EIP champions, they have all these ideas, but they never actually do the implementation bit. And this would already get you a long way. Like if you now come on and say, OK, I have this EIP, I also already have a prototype implementation, it's better than nothing, right? People can look at that, people can play around with it. You actually show that it's, like you demonstrate that it is implementable, right? So I hope, I don't know. Again, this was a little bit experimental. I did see a lot of people glancing over a lot of the presentation. yeah, I have total understanding for that. So it's a little bit specific to this EIP. If you're not interested in the EIP, maybe this was not for you. But if you were, maybe this was interesting. This is basically all there is to it, like implementing an EIP end to end, including the testnet, including everything. We could even ideally maybe try, we have like a testnet with multiple clients running. We could even try and just connect this node to it. It could just work. I think our testnet is not yet on Berlin. I think it is. I'm not sure. So maybe not, but yeah, that's basically all there is to implementing an EIP in a prototype quality. So thanks. Yeah, any questions or feedback or?
I have a question, not on the technical side, but when is it acceptable to make a pull request to propose an EIP? Like what's more the social process?
Right. So there's of course different things. So like if there's one just pull request against Geth in general. So like if you see an issue or something you want to improve, that but not change the protocol, just like a small improvement in Geth, you just as long as it's production quality, they're always happy to have PRs. They might not look into it immediately, but that's always, you can just go ahead and do that whenever you see something in Geth you want to improve. For actually changing the protocol, though, of course, that's a quite different thing. And so there, the process isn't even through Geth at all, right? So Geth, all they do is they only implement whatever Ethereum as a whole decides to do. So first thing would be to actually get people to accept this EIP or whatever EIP you have onto mainnet.
So how do you propose an EIP?
Right.
Say I have a cool idea. How do I
Well, I mean, I could tell you a little bit about it, but we do also happen to have an EIP process expert sitting here. So Matt, if you want to maybe give a quick summary of the EIP process from inception to implementation.
So basically, once you have some idea that you think might make sense as an EIP, you would kind of talk with some people in the community and see if they also think that it makes sense. Usually, it's not good to just toss something out there that you're the first person to think of, because the collective community might say, oh, well, there was an EIP trying to do this, it didn't work out for these reasons, or other reasons. So once you get some community sentiment that's positive, you can write your draft EIP, and there's, if you go to the EIP repository, there's a pretty good description. EIP-1 will explain this is what you need to have in your descriptions, what you need to have in your specification, all these things. Once you write your draft EIP, you can submit a pull request to the EIP repository, and I will review it, or some other editor will review it. It will get a number, it will get merged, and at that point you can kind of take it to all core devs every 2 weeks on Friday usually. There's an agenda in the ETH1.0-PM repo that has the agenda for the meeting of the day. You can say, hey, I have this idea. I would like to discuss it with core devs. And so usually at that point you can get included in the meeting and then say, hey, hello core developers, this is this idea. What do you think? And at that point you'll either get yeah, this is something that makes sense, this is something that doesn't make sense, this is something that we want to do soon, this is something we want to do in a long time. And so at that point it's kind of up to the core developers. They have to determine is this secure, is this a safe upgrade? And then they also have to decide is this something that fits in this collective roadmap? Because Ethereum has this kind of collective roadmap of things that we want to do in the future, and it kind of needs to fit in with some of those things we want to do. We want to have the merge, we want to have state expiry, we want to do the counter extraction. And so if we're trying to go in many different directions, it's hard for client teams are limited in bandwidth. They can't ship every feature that everyone wants. And so this is where it gets really opaque about what goes into an upgrade. And so things that diverge from the holy path forward for Ethereum, yeah, this is not lost a little bit. So.
No, this makes complete sense.
Yeah. It's the EIP process is clear. The process of turning EIP into a hard fork is very opaque.
No, but this is kind of what I was expecting. So you just get some feedback, try to get some people to propose in it. Then when it's reasonably okay, if you feel it's okay, then you submit it directly to the EIP. Then they're gonna say, oh, who are you? Come up with this idea.
Yeah.
So you're free to go there.
Yeah.
In this process, I see that the client is coupled with the protocol, but there are other clients as well. So that you
What's the time? Did I run over?
Oh,
or-
That's
we're
like
a little bit.
Porsche.
Oh, okay.
Right.
Like 15 minutes maybe.
Oh, okay.
And they're like,
No, the all core devs is like client.
Sorry
Oh,
about
okay,
that.
okay.
Yeah, so like there's
so
like
they have a protocol team and that's it.
Okay.
yeah, I mean there's people like
So let
me
me
who like
just-
don't manage any clients and we like pretend we're like core devs by doing occasional PRs, but like there are real core devs who like have clients and that's kind of like their call for them to decide. They're kind of the ones who are, and you know, the thing is like they, for the most part, aren't the people who are like saying this is what we want to do in the future of Ethereum. A lot more of like what their job is like, you know, we have these clients, they're trying to solve problems, so things that exist today, things like state growth. And then there's like Ethereum researchers and a lot of Ethereum Foundation people who are like, these are places that we want to take Ethereum. ETH2 is a big research effort that hasn't really spent much time with like current client teams. So and there's other stuff like that. And so that's kind
Let
of
me
like
just
where
briefly tell them that if
this
they
is
want
like
to
the
find the
one
code, they
place
can see
where
it
all
in the
client
PM,
developers
then
are
we can
there
off
and
this.
they kind of say like, look, you know, we're the people who wake up at 2 a.m. when something goes wrong, and we can kind of tell you like if you're like, you know, researching proposals like something happen in the protocol.
Also, just briefly, last thing from my side, because before I hand it over here, if you actually want to find the specific code we wrote, I just pushed it, and so if you just find like my handle, Dietrichs, the Go Ethereum fork, and then I just created a new pull request. So now there are 2 pull requests. The first one, the target implementation, was the one I did in preparation for today, and then the other one is the actual code we wrote today. So you can find it over there. Yeah, that's all from my side.